Iowa State chapter, Sigma Xi. And as I said at our last meeting, the president doesn't do as much work as the president-elect, Tom Loniken, and he was one of the people sweating up here. Thank you all for coming. It's a wonderful crowd. How many of you are geologists? Geology students? And the rest of you are all something else. It's wonderful. Thank you so much. Well, Tom will introduce our speaker, who's probably still sweating.
Of course, I was over at 4 o'clock this afternoon. I set it all up. It worked great. Everything came up, and it's always under the pressure when it doesn't come up. It's my pleasure to introduce tonight Neil R. Iverson, who is our Sigma Xi lecturer. Neil is a professor in geologic and atmospheric sciences. He has a BS degree here from Iowa State, a PhD from the University of Minnesota. Neil's topic tonight is the sliding away, studies of the glacier movement and rock erosion beneath the Svartisen.
Close enough.
Okay, ice cap in Norway. Let's welcome Neil.
I want to thank Sigma Xi for having me to speak tonight, having me here to speak. We're starting off a little late, I guess, but fortunately I'm only going to talk for about 3.5 hours. It's always a pleasure to speak to an audience with a wide range of backgrounds, but it's also potentially disastrous because there's a tendency for researchers to go into way too much detail when they talk about their research. So I'm going to try to avoid that today, although I'm not going to make any guarantees. What I want to start out doing today is just talking in general about glaciers and why people in general should perhaps worry about them a little bit. Before I do that, and also talk somewhat about our research beneath this small ice cap in northern Norway, I want to acknowledge all the different people involved in this work, some of whom are in the audience. Pete Moore, for example, who's a student of mine right now at Iowa State. You'll see a picture of him later. I also want to acknowledge the National Science Foundation, who's funded this work through several different grants. So let's ask the question: why? How do I get rid of that little guy up there? Let's see. Whoops. Well, I'll try again. Okay. So why should you really care about glaciers? Well, the main reason most scientists care about glaciers is because they're really outstanding archives of past climate variability. And I'll give you a good example of that in just a few minutes. I'm going to talk a little bit more about the second one on the list there, and the fact that glaciers respond to climate change, and you all know that. But I'm going to talk about some ways they respond to climate change that are a lot more dynamic and probably interesting than what you usually think about with respect to glaciers reacting to global warming, for example. And of course that affects sea level rise as well by transferring land-based ice to the ocean basins. The reason I got interested in glaciers originally is for the simple-minded reason is that they're very beautiful. And to me, that's about all the motivation I need to study glaciers. Unfortunately, that's not enough motivation for a research proposal. But you definitely have to retreat to number 2 here to get any money to study glaciers. And of course, glaciers also produce really the most spectacular landscapes on Earth, and I'll show some of those as well. And of course, glaciers are also responsible for some of the most fertile soils in the world, including those of Iowa. Well, this is a plot that most of you have seen in some context or another. The yellow line that grades into the red line is the increasing atmospheric carbon dioxide since about the beginning of the Civil War. And then the noisy histogram in the background is the average northern hemisphere surface temperature since the beginning of the Civil War. And you can see that the two seem to correspond quite well. But as scientists, as appropriately skeptical scientists, we need to look at correlations like this and ask ourselves, are they really robust? Because this isn't really very much time. So wouldn't it be nice if we had some way to go back in time to look at these two variables, temperature and carbon dioxide, to really prove that correlation is robust? And of course, we do have a way to go back in time. We can go back several 100,000 years, and glaciers provide the mechanism to do that. Specifically, what scientists have been doing for the last several decades has been coring the thickest and oldest parts of the Greenland and Antarctic ice sheets. And what they're left with is this very long core that's miles long. And what they do is they look at effectively the geochemistry of the ice that's withdrawn and what's in the ice. And what I want to focus on are these little amoeba-like blobs in this thin section that you see up on top. Those are air bubbles. Those are air bubbles that are trapped in the snowpack when the snow falls on an ice sheet. And eventually that snowpack is compressed and recrystallized into glacier ice, the interlocking crystals that you see in that upper diagram. But what's neat is some of the air is trapped in the ice as well. And so what those are little fossilized pods of air, from some of them hundreds of thousands of years old. And so we can look at the chemical composition of that air and make a statement about how what the atmosphere was like a long time ago. There are lots of proxies, climate proxies, that can be gotten from ice cores, but the other one I want to talk about has to do with the oxygen in H2O. That oxygen, there are different stable isotopes of that oxygen, and the ratios between those stable isotopes turn out to be linearly proportional to the temperature of the atmosphere in which the snow originally crystallized and fell onto the ice sheet. And so, that is a proxy of temperature over the ice sheet as the snowpack developed and eventually turned into ice. And what you can see here then in the lower left are data from a paper in Nature that came out in 1999, which shows the correlation between carbon dioxide in the atmosphere and the temperature above the Antarctic ice sheet over the last 400,000 years. And you can see this remarkable correlation between those two variables. Now, in that left-hand plot, I can't even plot modern-day carbon dioxide on that plot because I don't have a tall enough axis on the right-hand side. And so we have to go to this other plot on the right with a stretched-out vertical axis on the right to plot the current carbon dioxide level in the atmosphere. And you can see that it's well above the carbon dioxide level in the atmosphere over the last several 100,000 years. And in fact, carbon dioxide levels today are higher than they've been for millions of years. And there's lots of speculation as to why these two curves match so well. But if you're just a blind empiricist looking at these data, it's pretty clear that as carbon dioxide rises, if history is any indication, there's going to be global warming that comes along with that. And so these are really good evidence showing showing the link between carbon dioxide and temperature. Okay, glaciers also respond to climate variability, and they do so in two ways. One's sort of the way that we teach introductory geology students, and let me talk about that. This is just a valley glacier, in a cartoon of the valley glacier. Of course, what happens on a glacier is snow falls up at high elevations, and over the course of a given year, not all that snow melts away, and so it keeps piling up in the upper part of the glacier. In the lower part of the glacier, over the course of a given year, there's net loss of ice. And so that's the part of the glacier that loses mass. And of course, if you're adding mass at the top and you're losing mass at the bottom, and the glacier isn't precipitously steepening with time, it's pretty clear that ice has to flow from the top to the bottom. And so that's what happens. Ice flows like this out to the front of a glacier. And when a glacier retreats then, what that really means is that it's simply melting at the front faster than it's flowing forward. And that's true of glaciers around the world, really, or most glaciers around the world, at least valley glaciers like this around the world over the last 100, 150 years. Let me just show you some examples. You may have seen comparisons like this before. That uppermost glacier is called Athabasca Glacier. That's in Jasper National Park. It's very frequently visited by tourists. Actually, all these glaciers are. But you can see how that glacier has melted back in the last 90 years or so. The second one is Grinnell Glacier in Glacier National Park. If current trends continue, there won't be any glaciers in Glacier National Park within 100 years. But you can see how big Grinnell Glacier was. It wasn't a big glacier but in the early part of the last century, but it was a big cirque glacier. You can see it's barely visible now from this same angle. It's still there, but it's behind that rock sill. In the third photograph you see here, a pair of photographs, is the Portage Glacier in Alaska. It's retreated a lot, as you can see, leaving a lake in front of it. And then that bottom picture is from the Austrian Alps. And in that case, the left-hand picture is from 1875, and the right-hand one is effectively the present. And the glacier can't even be seen today. And so glaciers around the world, for the most part, have retreated like this, at least valley glaciers. And that's mainly due to warmer summers since the Industrial Revolution. Warmer summers lead to more melting relative to ice flow to the front of the glacier, and as a consequence, the ice margin retreats. But there's something a lot more interesting than this that's been happening in the last few decades, and really we've only learned about with any certainty in the last 5 years. This is a more interesting response of glaciers to global warming. And this has to do with the big ice sheets, in Antarctica and Greenland. And it has to do with the fact that large portions of those ice sheets terminate not on land, but in the ocean. For example, in Antarctica, a lot of the major ice streams that drain the continent terminate in ice shelves, floating tabular bodies of ice that in some cases are over 1 kilometer thick. Now these ice shelves, not everywhere in Antarctica, but in some places, they're breaking up at a very, very high rate. Now when an ice shelf breaks up, because this is ice buoyantly floating in the ocean, that doesn't raise sea level. But here's the interesting part. When the ice shelf breaks up, it was formerly exerting a back pressure on the ice that's farther inboard. And so when the ice shelf goes away, the ice streams speed up. And that's been observed now and documented very well in several locations, where ice streams have speeded up by a factor of 2 or even 3 in response to ice shelf breakup. The reason the ice shelves are breaking up is because atmospheric temperature is rising and ocean temperature is rising, and the ocean water circulates beneath these ice shelves and melts them from below. So, if the ice streams in the continent are moving faster, that means a larger flux of ice is moving to the ocean basins. That raises sea level. There's another effect as well. It's also a dynamic effect. But let me give you an example of what I just talked about first. This is Antarctica, of course. Antarctica has 3 sectors. East Antarctica on the right there, that's the big part of the continent to the right of the Transantarctic Mountains that run north-south. And then there's the West Antarctic ice sheet to the left in that map. The East Antarctic ice sheet is thought to be very stable. The West Antarctic ice sheet is losing mass pretty rapidly. We're not exactly sure where it's losing its mass, because the measurements that are used to measure its mass are gravity measurements. They measure the degree to which the ice sheet affects the gravitational field in the area of the Earth. And so we can't pin down exactly where the ice is being lost, but it is being lost at a high rate. Where the effects of global warming, though, are most conspicuous are out on the Antarctic Peninsula. Now, if the West Antarctic ice sheet melts, this is the way the south coast of Florida will look. About 18 feet of sea level rise, if that happens. Now, when I've showed this before occasionally in talks, I've made a lame joke about how I think this would improve the political landscape of the country if Florida would go away. But for some reason this week, I just feel pretty content. I don't know why. This is part on the Antarctic Peninsula, and it's an ice shelf. It's actually a fairly small ice shelf, but it's really impressive because in 2002, an area the size of a large Iowa county, ice 300 or 400 meters thick, that ice shelf broke up in just 2 months. And when it broke up, in the years subsequent, in the 3 or 4 years subsequent, all these glaciers in the mountains that flow down to the ocean have speeded up by about approximately a factor of 2. And so the buttressing effect of these ice shelves is indeed very important. It sort of holds the ice sheet together in a way. Now, there's another response to climate change that's more interesting than just the direct effect of melting, and that can be seen in Greenland today. This is, of course, an oblique view of Greenland, and what it shows are maps of the extent of summer melting on the ice sheet in 1992 and in 2005. So in 1992, what the satellite observed was that this was how far up on the ice mass the snow was clearly melting. There were pools of water and so on that could be seen from space. In 2005, this is where that same boundary was. So it's moved to a higher elevation, and the melting zone has increased greatly in size. So what does that do? It means that all this meltwater is being produced in greater quantities, and a lot of it, not all of it, but a lot of it dumps into big holes in the ice like this and ends up down at the bottom of the glacier. And when it sits at the bottom of the glacier, in a very general way, it behaves kind of like a lubricant, and it allows the ice to move faster. And so all the glaciers around the southern two-thirds of Greenland, for the most part, are accelerating, and they're moving, and they tend to have their ends, again, grounded at or below sea level. And so, again, the ice along the margin of Greenland is slipping away into the ocean in a very general way. And that ice is retreating as well. This is Helheim Glacier along the coast of Greenland. It's what we call an outlet glacier. It flows through mountains to the north and to the south here. But you can see how much it's retreated. This is a fjord covered with icebergs. Here's the glacier moving from left to right. And you can see the margin in 2001 was here, and in 2005 it was something like, 5 miles further up glacier. Some people think this retreat causes a feedback that makes the glacier move faster. Because this ice down here, when it was a coherent ice mass, again, was probably helping to buttress the ice farther up glacier. Now that it's gone, the glacier starts accelerating and moving faster, and that much higher a flux of ice gets to the ocean. So, one reason to be interested in glaciers is that they're speeding up. And that's the main effect of glaciers right now on sea level rise. It's not the direct effect of melting. The other reason for being interested in glaciers is the outstanding topography that they produce. The great mountain belts of the world wouldn't look anything like this if it wasn't for glaciation. There'd be these sort of rounded blob-like mountains with relatively unspectacular river valleys dividing the blobs. In the case of mountains that are glaciated, you get these very steep valley walls, these big bowl-shaped features called cirques, horn peaks, knife-edge ridges, big, broad, flat-bottomed valleys. I'm tempted to suggest that mountaineering probably wouldn't even exist as a sport if it wasn't for glaciation. In particular, it's glacial erosion, of course, that takes a river valley and scoops it out and makes the topography a lot steeper. Glaciers, of course, also have affected our landscape here in the Midwest, which maybe isn't quite as spectacular, but the glacial imprint is really just as conspicuous. Here we have what's called a drumlin field. This is a particularly good one north of Madison, Wisconsin. You can see we have these elongate hills. They're all kind of parallel to one another. And it turns out these things form not against the glacier out of its edge, but underneath the glacier. And most geologists believe at this point that they're mainly erosional features. They reflect the fact that the sediments that the glacier was sitting on have been eroded away in between the drumlins. And of course, the drumlins have sort of been sculpted by the glacier flow as well. Note these farmsteads here for scale. These are pretty large hills. Nobody really knows how drumlins form because nobody has a really good grasp of what's going on beneath glaciers, at least not to the extent to devise sort of convincing theories for how these form. And finally, I just wanted to mention soils briefly. Frankly, I don't know a lot about soils, but I do know that, at least I think I know, that in for example, southern Indiana, that hasn't been glaciated, this is the kind of soils they have. They have very thin residual soils with bedrock right up near the surface, a fairly anemic, infertile soil layer. In Iowa, of course, glaciers erode rock, but they've got to dump the rock somewhere as well. And Iowa, for the last 2 million years, has been a big dumping ground for glacial sediment. And so the soils of Iowa have developed by weathering on these thick sediment layers, and that's part of the reason they're more fertile than they are in southern Indiana. So although in southern Indiana they can grow lots of tall basketball players, they don't grow many corn and soybeans, apparently. Now, this is more along the lines of what our research program is involved in studying, and that is glacier movement. I was talking about glaciers speeding up. And glaciers can move in a variety of different ways. One way they move is by the ice deforming internally, just like water in a stream in a way, only the ice behaves as a much more thick or viscous fluid. You may not think of ice as a fluid, you think of it probably as a solid, but when you take a solid and you get it right up near or at its melting temperature, it can deform in the solid state, just like a fluid. Rocks deep in the crust are doing that right now as I speak. And so, because they're hot, they're warmed up near their melting temperature. And that's the way ice is on the Earth's surface. And so it deforms under its own weight in the direction that the ice surface is sloping, such that if we put a marker in the ice and came back a little later, it would have this kind of a shape. Turns out, though, that when glaciers speed up, like they have in the last several decades, it's not because of this kind of flow. It's because of stuff happening down here at the bottom. The ice can slip across the bedrock surface, such that it would be a displacement here from A prime to B prime of our hypothetical marker. Or a glacier doesn't have to sit on rigid rock. A lot of the glaciers that were in places like Iowa and Wisconsin and Minnesota sat on sediment layers. And in some cases, at least some glaciologists believe, that if we have ice sitting on very wet sediment, the sediment beneath the ice can shear such that this might be a kind of a velocity profile in the sediment, and the ice just rides piggyback along on that sediment layer. So we're interested in that process as well. And some people think this gives rise to the very fastest glacier motion. You've heard about glacier surges. Well, glacier surges are thought by some to be a result of glaciers resting on sediment. So here are some problems, more specific problems that we've studied, and then I'll talk about a little bit. Glacier movement over a rock bed, glacier movement over sediment, and then I'll talk about erosion of bedrock. Let me expand on those ideas just a little bit to give you a flavor of the kinds of hypotheses we're interested in testing here. First one is glacier sliding over rock then. It's really not hard to understand why glaciers slide over their substrates. If we take a block out of the freezer and we put the block, say, on this table and let it warm up, we know it's going to warm to its melting temperature, and we know just from experience spilling ice cubes that we're going to get a layer of water beneath the block. If we then tip the table a little bit, we know the block's going to not only move, but it's going to accelerate right off the table. Now, when something accelerates, that means there's a net force acting on it. That means that the driving force associated with gravity is exceeding the resistive force, the resistance to slip down at the bottom of the ice block. So it's not hard to see why glaciers slide. What's harder to see is why they slide so slowly. What slows them down? What keeps them from accelerating catastrophically like this? What holds them back? And it turns out that the leading hypothesis for this goes back to a material scientist that worked about 50 years ago named Wertmann. And he considered the obvious fact that glacier beds aren't smooth like a table, but they have lots of bumps on them. And he was able to quantify the effect of how ice moves around these bumps by deforming. And the bumps then exert a drag on the ice in the up glacier direction, which slows the glacier down, keeps the forces, driving and resisting forces, basically in balance. Now, what's been neglected in this process is the fact that ice contains lots of debris down at the bottom. Glaciers contain debris at their beds that's been eroded from the bed. And that debris tends to move across the rock and be in frictional contact with the rock. And so one of the things we wanted to do was study this friction, because people had neglected it for the most part, and we wanted to see if it was really should be neglected in mathematical models. So that's one thing we were interested in. Another thing we were interested in was the movement of ice on sediment. This is the sort of paradigm that's operative right now. The idea that the sediment shears beneath the ice, kind of like a deck of cards. If you push on one side, the cards slip over one another. In this case, the particles of the sediment would slide past one another. But we were interested in what might happen if we did an experiment like this. Would the ice really deform the sediment, or would it slip across the sediment? Now, you might think that sounds like sort of an esoteric thing to study, and I guess ultimately it is. But it is of interest because, of course, if glaciers deform their beds like this, that means most of the sediment that, for example, came into Iowa came in a deforming bed, not in the ice at all. So it really changes our viewpoint of how glaciers move sediment, depending upon which hypothesis is correct here. So we wanted to study that problem. And then we wanted to understand glacial erosion better, erosion of bedrock. This is bedrock out in front of the glacier I'll be talking about in a few minutes. And flows from right to left. And it really illustrates the two main erosional processes beneath glaciers. First of all, on the upstream side of this bump, you've got debris in the ice, and it's scraping across the rock and smoothing it out. So this is the up glacier side. You can see scratches, in fact, on this rock. But on the down glacier side, when we're... Oh, man. Unfortunate. I suppose that will... Wonderful. Sorry.
We still got a picture here, don't we?
We still have a picture here, so it's the projection.
Push that white one. The lower one.
I think it's this one. I think so. No, do we know what our technician did?
Yeah, I think so. It may take him a while to warm up. He hit Shift F8. Now turn this off.
It sort of stutters there a second. Tell you what, maybe I should keep forging ahead here.
Nice photographs. We hate to lose those.
Does anybody have better knowledge than we do? Oh,
No, it's still searching.
there. Well done. Okay, sorry about that.
The younger they are.
So I was talking about erosion on the downstream side of this bump, which has a funny name. They're called roches-moutonnées. And what happens on the downstream side is cracks in the rock that are pre-existing. All bedrock has cracks in it at various scales. And because of loading by the ice, the cracks slowly grow, just like the crack in the windshield of your car. And eventually they coalesce and isolate rock blocks, and those rock blocks are pulled away by the glacier. So we wanted to understand that process in particular, because no one had really studied that process through any kind of field measurements. And it's by far the least understood process of erosion, and it's the most important. It's probably volumetrically the most important. And in particular, we were interested in understanding the variables that controlled the rate of crack growth in the bed and how rock was eroded. Most models assume that it's just a function of the sliding speed, how fast the ice is sliding across the rock. We were interested in testing a different hypothesis, which stems from work I did years ago, some numerical modeling in my dissertation. If water pressure at the bottom of a glacier is high, due to the fact that lots of water is pouring in from the surface, such that there's kind of a water table, in a sense, in the glacier that rises and increases the pressure at the bottom, what will happen is the ice will tend to separate from rock on the down glacier side of these bumps. And when the water pressure then fluctuates, as the water input fluctuates due to daily and seasonal melting variations, what that does is it sort of fluctuates the pressure that the ice exerts on the rock here, and that we think can cause the cracks to grow. It's sort of a fatigue process, like if you took a metal wire and you moved it back and forth enough, it eventually cracks. Well, in this case, if you cycle the water pressure enough, we think we can grow these cracks in the rock. So we wanted to test that idea. So let me move on now and talk sort of in a fairly cursory way about our work, and hopefully not get into too much detail. This is the Spartacus ice cap, and it's right here. It's at about the latitude of the Arctic Circle. The North Atlantic is this plain where we took this photo is probably over the North Atlantic at this point. Here's a fjord that runs up to an outlet glacier right here. And what makes this glacier unusual is that there are tunnels in the rock beneath the ice that were made in the mid-90s. And the reason there are tunnels is that there's a lot of water that flows at a high elevation under this ice cap. And that water is channeled. Unbelievable.
Don't touch the computer.
Just barely.
It'll stay inputted. You just have to start up the projector again.
So I shouldn't plug?
No, you gotta plug it back.
You set it up just like that so you trip to it.
Yeah.
And then just don't worry about your computer. It should still be inputting because it didn't get unplugged. And then if it doesn't start up.
So this ice cap then has all these tunnels underneath it. And there's water flowing beneath the ice cap, and that is routed to a hydropower station at the head of one of the fjords that was in that photograph.
Are the tunnels man-made or natural?
No, they're man-made. They were blasted beginning in the late 1980s, and they were finished by about 1995, I think. But in any case, some of these tunnels beneath the glacier are dry. Here, now, I'm going to stay away from there. Some of them are very wet, filled with these roaring torrents of water that move to the hydropower station right here. About 99% of Norway's electricity comes from hydropower. But some of them are dry, and we've used some of those dry tunnels right beneath the glacier here, where the ice is about 700 feet thick, to do experiments on the processes that I've been talking about. There you go. Now I'll bump the chair. This is looking up one of the fjords, and it's a glacier, it's an outlet glacier of the ice cap called Engebring, named after the Engen family who lives outside this moraine, in the foreground here. They lived there for several hundred years, apparently. And this is where the ice was about 100 years ago, so it's retreated a lot and left this lake in its wake. But I'm really showing you this slide to show you where the tunnel entrance is to the whole tunnel network underneath the ice cap. This is just a slide showing how we get up there. Sometimes we walk up, but if we're going to be up there for a long time, sometimes we're up there as much as 3 weeks or a month. In that situation, we get a helicopter ride, and the food is taken up in a hanging load like this. Now, although all these boxes are banana boxes, that of course doesn't mean we eat only bananas. Although the diet isn't too much more diverse than that. This is the tunnel entrance up on the mountainside. And here's a schematic of the part of the tunnel system that we use. Inside this tunnel are living quarters for visiting scientists. If you walk about 45 minutes up the tunnel, you get to a laboratory that has some basic analytical equipment. And then, most importantly, there's this tunnel that runs up right to the ice-rock interface. There are 2 access points to the bottom of the glacier, a vertical shaft and a horizontal tunnel. I'll talk about this tiltprism in just a few minutes. Now, sometimes, when I was here in '93, when they were blasting this tunnel, they would get too close to the bottom of the glacier and they'd open up a portal to the bottom of the glacier so that there was ice sitting right above the tunnel at atmospheric pressure. And this is my slide to convince you that ice behaves like a fluid. The ice deforms in the solid state and just gets extruded from the base of the glacier into the tunnel as a big ice plug that you see here. This happened in only about 10 days. So under the conditions that sort of apply, particularly at depth in a glacier, ice definitely behaves like a fluid. What I want to do now is show you a picture looking right up this shaft at the base of the glacier. The cap to the shaft has been taken off. If we didn't have a cap at the top, the ice would just squeeze right in. This is gneissic, sort of schisty bedrock. And this is the bottom of the glacier. It's not blue ice, it's not white ice, it's in fact brown ice. And the reason it's brown is it's filled with debris, about 10% debris by volume. You can see some sort of grapefruit-sized cobbles among the finer particles. Now, what we do in some of these experiments is we make an instrument. I won't talk about exactly what it is yet. We winch it up this shaft so that it's pressing against the bottom of the glacier, and then we support it underneath with these steel legs. Now, one of the things we're interested in is how much real friction is there between this sliding ice, which happens to be sliding at about 4 inches per day, and the underlying bedrock. This is ice, not rock. It's ice with about 10% debris. This is clean ice up here. So how much friction is there down here? Glaciological modelers assume there's zero friction down there. So we built this device that we winch up that shaft. It's just a granite tablet with a bunch of transducers inside the panel. And what we measure, most importantly, is the force that the ice exerts tangent to the rock, which tells us basically what the friction is. This ball here is picked up by the ice and carried along. It's connected to a wire which runs down into the shaft. And as the ball is drawn out, the transducer measures the rate at which the wire is drawn out, and we can get sliding speed that way. Now this is that instrument when it's in place. These are the electrical cables. You can see all this water condensing at the bottom of the instrument. It's very moist in these tunnels. It's about almost 100% humidity. It's about 2 degrees C in these tunnels. Of course, it's dark, but it could be worse. One thing about the tunnels is the weather is very predictable. It's pretty much the same thing. This is the instrument when it came down. We were afraid it might get plucked out by the glacier, because once we had it up there, we realized, we didn't really connect it to anything, so if the glacier pulled it vertically somehow, it would get removed. But it didn't, and so my colleague Denis was quite relieved when it came down. Denis is French, and of course the French sort of behavior comes naturally to the French. Denis lives in Switzerland, so he never is at these talks, so I can pretty much make fun of him to any extent that is expedient. This is the panel that I just showed you a photograph of. I'm not going to show you how it works. There's the debris-rich ice sliding across it on top. And let me just cut to the bottom line here. Friction on this tablet was about 20 to 50 times higher than we expected, based on the leading model of friction. People had tried to mathematically model that friction, and they were literally off by 20 to 50 times. And what that means is that it's not just the bumps on a glacier bed that slow it down. The debris content is really important as well. And the more interesting question from a scientific perspective is why? Why is the friction so high? I don't want to go into a lot of detail here, but if you consider a rock particle in ice like this, surrounded by ice, resting on a rigid bed, the basic question is, why does this particle press so hard on the bed? Because that's what gives all the friction. Well, it has to do with the fact that the ice is melting at the bed due to frictional heat and geothermal heat. So the ice is melting. That means there's a component of ice velocity downward past the particle. And remember, ice is a fluid. And when fluids move past objects, they exert a drag on that object. And so this ice moves downward past these particles, exerts a drag on the particle, which gets imparted to the bed. Now, we didn't come up with that. That was in the earlier model. But what we did is numerically model the flow in this situation. And what we found is that very low pressure develops in the ice down here, and that leads to a very high drag force. And so we could reproduce our results theoretically with this numerical model. Now, the other question, another situation. Ice, instead of resting on bedrock, now it's resting on sediment. We wanted to study that situation. Well, the problem is beneath this glacier, the bed is rock. It's not sediment. So the first thing we had to do is make a synthetic glacial till from the tunnel sediment, from the debris at the bottom of the tunnel that was really a result of blasting. Till is a kind of sediment that melts out of ice that has many different particle sizes. Fortunately, blasting produces many different particle sizes, so it was easy for us to manufacture a till. We then wanted to emplace it at the bed between the ice and the rock. In order to do that, we melted a tunnel along the bed using a system I'll show you in a minute to a flat spot. We then blasted out a trough in the rock. We filled it with this synthetic till, put lots of instruments in it to measure stuff. Then we got our bodies out of the tunnels. We let the ice close viscously down on the sediment until it was sliding across the sediment. And then we did the most important thing. We pumped water from below up to the sediment wedge to vary what's called the pore water pressure in the sediment. As the pore water pressure goes up, the sediment weakens. And what we wanted to know is if the pore water pressure got high enough, would the ice slide across the sediment instead of deform the sediment? Because that's important. Glaciers that have sediment at their beds like this have very high pore water pressure in the sediment. So we wanted to reproduce that situation. This is the door to the bottom of the glacier. This is that horizontal access tunnel I mentioned. This is melting an ice tunnel with the warm water drilling system. This is water at about 60 degrees C. This isn't one of the more pleasant jobs there. And this is what's produced. A tunnel that's, a couple meters tall in this case and maybe 1.5 meters wide. And my colleague here is sitting on bedrock, abraded bedrock I might add, in a quarried spot over here. I have these arrows drawn in here because this ice is thick. It's about 700 feet thick. So when you open up a void at atmospheric pressure, the ice squeezes in. And that was something that was relevant because sometimes our hot water drill would break as we were trying to set up an experiment. And then there'd be this period of great tension as we tried to fix it and get it working again because all the time the ice is closing in at a rate of about 0.5 meter per day. This sometimes led to some fairly desperate measures to keep these tunnels open. Denis isn't that strong. This is what the Till Prism looked like when the experiment was just getting started. At least this is what we hope it looked like because we couldn't actually see it. It's about 2.5 meters long and about 2.5 meters wide and maybe 0.5 meter thick. We had lots of instruments in the till, and I'm not going to show you any time series from those instruments or anything. But I will tell you this. As we pumped up the pore pressure in this Till Prism, first the till deformed, like sort of the dominant paradigm would predict. But then, when the water pressure got within several hundred kilopascals, that's a column of water 20 meters deep or something like that. When the water pressure got high enough, the ice slipped across the sediment, and the sediment relaxed elastically and sheared. It's sort of like rocks do along a fault during an earthquake. And so what this showed us is that when water pressure is high in a subglacial sediment, as it often is, because it's hard for water to drain through a very impermeable till, it requires a steep hydraulic gradient to drive it out of there. Pore water pressure is high, we think that the norm is for ice to slip across a till surface rather than deform it. Let me just talk a little bit more about the living situation in this tunnel. This is the kitchen, where there's a 2-burner stove where we've sometimes cooked for as many as 14 people in here. This is a Norwegian named Nils Håkansson, who is a really good guy, but he spends about 200 days of the year out in the field, on or under glaciers. And it's made him somewhat rough around the edges. It's given him some somewhat distracting habits. And one is that while he cooks, his nose tends to drip. And those are two processes you really don't want going on at the same time. The other thing I want to comment on here is about the food. My distant ancestors are Norwegian, but I confess that I don't seem to have any genetic disposition for Norwegian food, the way they eat it over there. For one thing, they put lots of food in tubes like this that you wouldn't expect to see in a tube, like caviar, for example, and processed cheese in a tube. This caviar is more sort of like a paste. I don't really think it's caviar. It's more of a fish that's been sort of ground up in a blender, I think. This is herring, and this is sort of rubbery herring and raw onions floating around in a mysterious fluid. And of course, cheese. They eat huge volumes of cheese. And to counteract the effect of that cheese on the digestion, they eat huge volumes of this Vasa bread, which is extremely granular and fibrous. So this food is something we talk about a lot when we're there, when we're not working, usually disparagingly. This is the last experiment I want to talk about. It consists of trying to understand crack growth in rocks beneath the glacier. People have not measured crack growth in rocks beneath the glacier, and we wanted to see what controlled how fast it occurred. And so this is another panel that was built and hoisted up to the top of that shaft. This is a granite step, and the ice flowed from left to right across this step. And what we did is we put a crack in it. We sawed a crack a few millimeters wide and several centimeters deep. And the reason we did that is that all natural rocks have cracks in them. And the issue is how fast do they grow. And by introducing a crack, we could also better interpret our data. At any rate, what we did then is we wanted to measure the rate of crack growth. And to do that, we couldn't do it directly because we couldn't see this while the ice was flowing over it. So we put what are called acoustic emission sensors along the sides of the rock and under the rock. And what they measure are the little waves that are produced when a crack grows. Even a little bit in rock, there's a little elastic strain in the rock that's relieved, and that sends out a wave through the rock. kind of like an earthquake wave. And these things sense when those waves arrive. And if you have a lot of them, you can use what amounts to sort of a complex triangulation scheme to figure out where the waves came from. So we can track the locus of this crack as growth occurs at its end. So what we did is we hoisted this up to the top of the shaft, and then we pumped water to the back of the glacier, to the back of the pump, downstream side of this pump, so that ice would separate from the downstream side. And then we would turn off the pump and let the water pressure diffuse away. And then we would turn it on again. So we would cycle the water pressure in this cavity, and we would observe what happened to this crack. Well, when we didn't introduce any water, we just let ice slide across the rock, there was no crack growth at all. We saw some acoustic emissions, but they were coming from the surface of the rock due to rocks in the ice scraping along the rock. But once we started cycling the water pressure, we started getting acoustic emissions. And with time, as we move here from cold colors to warm colors, those acoustic emissions started up here, and then they worked their way down. So that it looked like a crack over about a 3-day period was propagating through this rock down to the base of this step. And that happened as, of course, the water pressure was fluctuating back here. And the reason for that is that for example, if you have water in here at some pressure, and you let the pressure go down, that's like having some big strongman push up on the ice and then quit pushing up on the ice. That shifts the weight of the glacier over to the rock and makes the crack grow. And this is what it looked like when we brought it down from the bed. Surface had been produced about along the trajectory of what the acoustic emissions suggested, and a piece had been quarried from that lee surface. What did this suggest? It suggests that if we want to model rock erosion beneath the glacier, if we want to claim we can quantitatively model how fast a glacier is going to erode bedrock, we can't just use models that are convenient. We have to actually use models that are physically correct. And we think we have to factor in these water pressure fluctuations in order to do that. So let me finish up here. I want to leave you with some things to remember. Probably the most important thing to remember is that glaciers are really fantastic archives of past climate change, at least if you're interested in climate change over the last several 100,000 years. Lots of glaciers in Antarctica and Greenland are speeding up right now, and it's that speed up of glaciers to the ocean basins that's raising sea level. That's the biggest contributor, at least from glaciers. There are other contributors to sea level rise as well. And when thinking about glaciers speeding up, and when thinking about erosion of the landscape, for example, all the action occurs down at the bottom, at the bed. And so that's the motivation for studying bed processes. And I've shown you a little bit about how we can use field experiments conducted in real time to try to test some important parts of that problem. That's one of the nice things about glaciology is things happen fast enough that you can actually do experiments in real time. In a lot of geology, we have to just look at the geologic record and make the best guess we can. In this situation, we can actually do experiments and try to definitively test hypotheses without quite the uncertainty that we're left with if we have to go back millions of years into the rock record. So, with that, I'll thank you for your patience both with the technology and my clumsiness. And if you have questions, I'd be happy to answer them.
Estimated that about 20% of all the fresh water in the world is in the Great Lakes.
Is it that much?
About that much.
Yeah.
About another 20% in Baikal Lake in Russia.
Mm-hmm.
Another 20% in Amazon basin. If you take those as a standard, how much of a fresh water is attracted here?
Well, actually, your data contradict what is reported about ice sheets, because what's usually stated is that about 80% of the world's fresh water is contained within the Antarctic ice sheet and Greenland combined.
What I was telling you was the water that is flowing. Now,
Okay, so the liquid water, sure.
Compare with
Yeah.
those, how much?
Yeah, okay, so the answer is that that's a relatively small volume relative to what's contained largely in Antarctica. Antarctica is much, much bigger than Greenland.
In monitoring the cyclical changes of climate in these glaciers, are there any indicators that signify a regression of the CO2 of the global warming inside the glaciers?
Regression of CO2?
Or the regression of temperatures and kind of the cooling back down?
In the future, you mean?
No, has it always kind of been rising since in monitored in glaciers?
Well, no. I mean, it's very, very cyclic. Over about the last 800,000 years, ice ages have occurred at a frequency of about 1 every 100,000 years. And, you can see, there's an ice core now that goes back almost 900,000 years. And you can see fluctuations in CO2 and temperature through all that period. So yeah, it's not just a rising, it's a system that's fluctuating up and down. And we have to think about the global warming we're inducing right now as, of course, superimposed on some natural cycle. But it is sobering to think about how high CO2 is in the atmosphere now and how it hasn't been that way for millions of years. And so when people commonly say that we're conducting a big experiment with the atmosphere right now, we really are. We really are.
These fluctuations in CO2 that have occurred over the hundreds of thousands of years, is that due to CO2 emitted by volcanoes, or why does it fluctuate?
Well, that's a huge question that people are working on, and there isn't a definitive answer to that question. There's lots of possibilities, and the biologists sort of like their scenarios, and there are more sort of physical scenarios as well. And I can't tell you what the leading hypothesis is for why CO2 is fluctuating like that. And of course, it could be a two-way coupling too. It could be that temperature is in turn affecting CO2, and so CO2 is affecting temperature, but temperature has feedbacks in the biosphere, results in feedbacks in the biosphere and whatnot that can affect CO2 production. So it's a very complicated problem. It's a two-way coupling. It's not a very good answer because I don't really know the answer.
I think what you're saying is that as the temperature goes up, plant growth accelerates, and this would take up carbon dioxide.
Well, I mean that's one possibility, but there are lots of other greenhouse gases as well, of course, like methane. Methane is actually a much more potent greenhouse gas than carbon dioxide, but it's present in the atmosphere at a lot lower levels, and there are lots of people studying how methane concentrations have changed in the past and trying to find the mechanisms for that.
What about water vapor?
Excuse me?
What about water vapor in the atmosphere? How is that?
Well, water vapor is the most effective greenhouse gas, but that's something that we don't view as having changed a lot in any systematic way.
But as temperature rises,
Sure.
pressure of the water.
Yeah, and of course it's very spatial, right? There are going to be different effects in different places on Earth. But I haven't seen any hypotheses suggesting that it's a water vapor modulated system going back through the ice ages.
What's the prediction on the life of the Ross Ice Shelf at this point? I mean, people think that it's going to go pretty soon, or 100 years, or what's the...
No, it's more robust than that. It's shrunk a lot in the sense the glacial maximum, 18,000 years ago or whatever. But it's relatively stable right now at its front, and in fact the ice streams, at least some of the ice streams that feed the Ross Ice Shelf, are not undergoing this acceleration at all that I was talking about. Some of those big ice streams are slowing down, like Ice Stream B is slowing down. So, again, in Antarctica, where the most conspicuous effect of warming is on the peninsula, and that's what's experienced the biggest increases in temperatures.
kind of a completely different nature. When you were at the bottom of the ice,
Mhm.
was it quiet or were there noises?
You can
It
hear,
was like scraping and...
when you're in the ice tunnel that you've made, you can hear popping sounds now and then. And you can sometimes hear bubbling sounds as water is moving from one cavity to another. But if you could somehow be in the ice and listen without having made a cavity, you'd probably, well, it's not unclear to me what you'd hear, because I think when you make a cavity, you cause lots of cracking in the ice due to the fact, just like when you're in a mine, sometimes the walls of a mine will kind of explode almost because there's so much pressure on them, and you've made this cavity at atmospheric pressure. And so the ice definitely is sort of actively adjusting and cracking when you open up these big voids in it. So I'm not sure. I think you'd still hear the water without the tunnel, though.
Well, a really interesting presentation under some trying circumstances. Cider and cookies. We don't want any of that left.
Neil, that was nice. And a nice audience.
Yeah.
Enormous audience.
Yeah.
What's happening to Kilimanjaro?
They're going to be gone real soon. I mean, 20 years. That's the estimate, is that the ice on Kilimanjaro will be gone in 20 years.
Now, at the latitude of Kilimanjaro, so you get to the area that's anything above 15,000, 16,000 feet. Is the area of the permanent snow. Where moisture gets up there, comes down.
Yeah.
Now, isn't this additional annual increase in the amount of ice and snow that builds up there substantially less than what is melted?
That collects up there?
You get a paycheck and you spend your money. Now, if you get $100 and you spend $100, paycheck bank account works the same. Now, but let's say you take in $100 and you spend $90. Now you have an accumulation. Now, ice on the peaks of that is the same thing. Every year it comes some down,
It's
and
always,
the other it melts.
right.
Now, is the difference between what precipitates there?
So we messed it up.
We'll see, because it didn't get on the board from the projector, it was still upping. So when you press the function of it in, you took it away.
Oh yeah. I mean, that's always when a glacier retreats like that. It's always because of that change in the balance.
That's
The
going
only thing that was unconnected was the
And what's causing the ice to go away in places like Kilimanjaro again are the higher temperatures. It's not as if they're getting less snowfall; they're getting higher temperatures. And snowfall might actually even go up a little bit because it tends to snow more in moister, warmer air. But what's happened in most of the world's glaciers is that warming, that summer warming, has resulted in the retreat of glaciers because it hasn't been compensated by any increase in snowfall.
You showed a picture of that Norwegian that spent
And it depends though on what you started.
Yeah.
If you started that and it was already plugged in when you started the laptop, that makes a difference because then the laptop reads the frequency.
He doesn't spend, the longest anybody spends in those tunnels is about 4 or 5 weeks. And that's not in the summer, because in the summer it is dangerous. There's water that flushes through the system. But that guy spends most of his time on the surfaces of glaciers, making surfaces of glaciers, making surfaces of glaciers, making